Hello, my name is Gaurav Pamar, and today I'm going to present our work ReTRACe, Revocable and Traceable Blockchain Rewrites using attribute-based cryptosystems. Before we begin, here's a quick overview of the presentation. I will start by introducing the problem and discuss our motivations for this work before briefly going over the related work. After that, I will discuss our contributions and the highlights of our proposed system ReTRACe, along with the novel cryptographic components RCHED and RFAME that were used to build ReTRACe. Finally, we will go over the evaluation of our scheme and its components before concluding the presentation. Knowledge about blockchains is fairly common today, owing to the craze surrounding cryptocurrencies like Bitcoin and Ethereum, among others in our current zeitgeist. Traditionally, blockchains are append-only ledgers with no modifications allowed. This is desirable in cryptocurrency transactions, as obviously we cannot give users the power to override or rewrite financial transactions or unilaterally change the terms of contracts. However, what we focus on in this work is a new class of emerging applications that not just require, but necessitate modifying data written to a blockchain. More and more solutions are being proposed in different fields of research that would utilize blockchains for storing data or exchanging information. For example, data from IoT devices posted on a blockchain, and Corda, a recent blockchain-based interbank transaction platform pioneered by R3, which is a consortium of financial institutions across the world. Let us consider the example of a consortium of companies such as banks and a rogue or soon-to-be terminated employee that posts other users' private information on the blockchain. While spam transactions might be a nuisance and can be ignored, in some situations, we cannot simply ignore bad transactions and need to proactively remove them from the blockchain. For example, objectionable content and personally identifiable information like social security numbers. GDPR compliance of shared data in applications such as IoT networks using blockchains is another example. Motivated by all these scenarios, there's a need to support redaction of sensitive data from blockchains. As mentioned before, our paper presents novel cryptographic primitives that introduce revocability in chameleon hashes, as well as ciphertext policy attribute-based encryption schemes. Hence, we divide our related work into two parts. Firstly, cryptographic primitives, which list the respective related work in the fields of chameleon hashes and ABE schemes. Secondly, we list the related work in the field of blockchain rewrites. While Krafchek et al. Were the first ones to introduce the concept of chameleon hash functions, Kamenish et al. Proposed a chameleon hash scheme that uses two trapdoors associated with a digest, a permanent long-term trapdoor and an ephemeral trapdoor. In this scheme, a message cannot be adapted without knowing both trapdoors. A downside of this scheme is that it does not support revocation. Once a user has access to the trapdoor, they can keep adapting the message indefinitely. Moving on to the related work in attribute-based encryption research. The encryption scheme proposed by Goyal et al. Has no support for revocation, and nor does FAME. FAME is a state-of-the-art ABE scheme that performs better in terms of qualitative and quantitative metrics compared to prior works and provides full in-CPA security. Hence, we use it as our starting point for designing an efficient and secure revocable CPABE scheme. The scheme proposed by Sahai et al. Has non-standard assumptions, only provides support for policy-level revocation, and CCA security is not possible in their scheme. Limitations of other schemes and related work, detailed in the full version of the paper, include having non-standard assumptions, requiring the use for revocation lists, or no support for type 3 pairings, etc. Next, we will briefly talk about the related work in the field of blockchain rewrites. Duber et al. And Repower propose mechanisms for block-level rewrites where any user can propose a redaction or edit of a block, which is then voted upon by all users, while Atomies propose a solution for blockchain edits by rewriting entire blocks using chameleon hash functions. These are coarse block-level rewrite solutions and are inefficient when a single transaction in a block needs to be updated. These schemes do not provide fine-grained transaction-level control of who is allowed to update individual transactions. Döhler et al. Proposed a solution where the trapdoor associated with a given digest was encrypted with a ciphertext policy attribute-based encryption scheme, but no revocation of access to the trapdoor was supported by their scheme. For a more complete comparison of the related work, we refer you to the full version of ReTRACe. ReTRACe has three major components: chameleon hashes, attribute-based encryption scheme, and dynamic group signature scheme. For chameleon hashes, we use RCHED, which is a newly designed chameleon hash scheme that supports revocation of the trapdoor. Attribute-based encryption is achieved by using RFEM, which is a newly designed attribute-based encryption scheme that supports efficient user-level revocation. The group signature scheme in ReTRACe provides authentication of messages and traceability of the signing party when required. We now outline our contributions in this paper before going into details of each of the components of a protocol in the following slides. We introduced two cryptographic primitives, RCHET, a chameleon hash scheme with the ability to update the trapdoor, and RFEM, a CPABE scheme that can provide efficient revocation mechanism for users revoked from their respective attribute groups. We refer you to the paper for the security analysis of our system and also provide experimental evaluation of the performance of our proposed scheme. Now we briefly talk about RCHET. A message in RCHET contains several components. The plain text message is represented here as M. The digest, RAN, pub, and priv components constitute the chameleon hash part of the message, with the digest being the only permanent component of the message. The verification function in RCHET takes as input the public part of the RCHET message, namely M, digest, RAN, and pub, and outputs a message confirming or rejecting the verification. The priv component of the message needs to be protected and not be available to the public, as it acts as a trapdoor for adapting the message and the trapdoor itself. In this slide, we show you the RCHET message changing between the different operations, namely message adaptation and trapdoor adaptation. As described in the previous slide, this is the structure of an RCHET message. A user with access to priv can call the adapt message function, which would output a RAN prime for a given M prime, thus modifying the original message to its new form, and this will pass RCHET verification. To exercise revocation, a user with access to priv can also call adapt trapdoor function, which would output a new RAN prime, pub prime, and priv prime for a given M prime. This modifying the original message to its new form and also adapting the trapdoor priv information to its new form. At this point, any user who had access to the original priv component will not be able to produce a new M prime and RAN prime that will pass verification, since the pub prime has also been updated and is used in the verification process. The verification of all RCHET messages always requires using the latest M, RAN, and pub values on the transaction to account for any adaptations that might have taken place since the message was originally posted. The priv component of the transaction needs to be protected using other access control techniques to enforce revocation of chameleon hash adaptations. In ReTRACe, we divide this priv component further into two separate parts. Anyone with access to the first part can adapt the RCHET message, and anyone with access to the second part can adapt the trapdoor and revoke access to adapt the RCHET message. Next, we talk about CPABE schemes. ABE schemes in the related work either do not provide for revocation of users from their attribute groups or provide revocation that is inefficient. For example, let's assume a system with 4 attribute groups, A, B, C, and D, with multiple users in each of those attribute groups. And there are 3 messages which are encrypted with the given policies. For example, for message M1, policy A and B, for message 2, B and C, and for message 3, policy C and D. In this system, a user from attribute group A is revoked. All other remaining users in A are rekeyed. This rekeying operation requires re-encryption of all ciphertext with policies containing the attribute group A. In this case, it's message M1. This updates message M1 to M1 prime. Since M1 prime got re-encrypted, users in attribute group B need to be re-encrypted, rekeyed to be able to access M1 prime. At this stage, users in A and B can both access M1 prime, but users in B getting new keys requires re-encryption of M2. And this mirrors earlier event from M1 requiring users in C to get rekeyed. This creates a domino type effect where in a system with enough messages with overlapping policies would in effect cause the whole system to be rekeyed. Needless to say, this is highly inefficient. The domino type effect outlined in the previous slide is avoided in RFEM scheme. In RFEM, when a user is revoked from an attribute group and the message is re-encrypted with the new public key of the AIA, the attribute groups in the policy who were not revoked will still be able to decrypt the data with the original keys. This avoids the need to re-encrypt messages having policies with the revoked attribute group, here messages M2 and M3. But the re-encrypted data in M1 prime cannot be decrypted with the old keys of the revoked attribute group or attribute group users in A. This is a high-level overview of the specific efficiency achieved in RFAME in the revoke operation when compared to the related work. We refer you to the paper for the detailed algorithms and the math supporting the scheme. Now, putting together the two previous schemes, RCHET and RFAME, we show how they tie into ReTRACe. Chameleon hashes help the transaction be adaptable. CPAB helps control access to the revocable chameleon hash trapdoor associated with a given transaction. GSS is used to sign all ReTRACe transactions and updates to the transactions. In conventional blockchains, hashes of entire transactions are used to build the Merkle root for a given block. But in the case of ReTRACe adapted blockchain, only the hash component of a given ReTRACe transaction is used in the Merkle tree. As hinted earlier, the priv component from RCHET message is broken into epsilon info and epsilon admin. Epsilon info contains information along with ABE encrypted trapdoor giving access to authorized users, AU, to carry out message adaptations. Similar to epsilon info, epsilon admin contains ABE encrypted information giving access to auth admins, AUA, to be able to adapt the trapdoor of the ReTRACe transaction. A given ReTRACe system will have three authorities: an attribute issuing authority, AIA, associated with the CPAB scheme, and group manager and tracing manager associated with the group signature scheme. The group signature scheme provides anonymity for users while ensuring traceability of bad actors, and as a tracing manager can be used to trace which member from a given group signature group produced a given set of signatures. The encrypted information contained within epsilon info along with the ABE policy enables users in AU to update the message. Similar to epsilon info, information in epsilon admin is only available to users in AUA and enables them to update the trapdoor. For a user to produce a valid ReTRACe update, they need to have keys to the attribute groups defined in the epsilon ABE, as well as the signing keys defined in the group signature policy epsilon GS. We use a Venn diagram here to depict the group memberships. In this case, user Alice, who has GSS keys for BizOps, can create valid signatures and has access to the trapdoor info to adapt the message from having the FIN and HR attributes from the AIA. However, another user, Charlie, who is also part of the BizOps group, cannot adapt the message, even though they can provide valid signatures from the GSS membership, since they do not have access to the trapdoor info. Both messages and trapdoor adaptations require verification on the miner's part before updating the given transaction on a blockchain. The first check is a simple RCHET verification of the message, hash, and RAND. The second step is to check that the group signatures provided by the message update satisfy the respective group signature policies defined in epsilon info and epsilon admin. A message adaptation in ReTRACe results in M and RAND components getting updated to M prime and RAND prime, while a trapdoor adaptation results in the epsilon info getting adapted and updated in addition. Just as a note, there are two kinds of trapdoor adapts in ReTRACe. Case one is when a policy of a ReTRACe message is updated to eliminate trapdoor access for an entire attribute group. And case two is when the trapdoor policy remains the same, but the user in one of the attribute groups got their keys revoked, and hence the trapdoor needs to be updated and re-encrypted with the new keys for the ABE scheme. We refer you to the paper for a detailed discussion about the two revocation cases. This slides detail the evaluation setup we use to carry out our experiments. We use desktop class hardware, and the schemes were implemented in Python using Charm cryptographic library. Now we will go over the evaluation results for our proposed scheme. We start with RFAME, which we compare to FAME, the state-of-the-art scheme. Encryption operations in RFAME have more modular exponentiations when compared to FAME, and the encrypt operation grows linearly with the number of attributes in the policy. The decrypt operation in FAME has a constant number of bilinear pairings, whereas in RFAME, the number of bilinear pairings in a decrypt operation depends on the number of decryptors satisfied attributes. The performance penalty in RFAME comes with the revocation efficiency, which would impact significantly in large systems. Intuitively, the cost of revoking a single attribute group grows linearly as the number of users in the group increases. And when it comes to comparing RCHET, there is no major impact in its performance compared to CHET, along with the added benefit of revocation. Here we have some timings demonstrating the scalability of ReTRACe for different trapdoor encryption policy sizes. As discussed earlier, case 1 represents policy level revocation, while case 2 represents a single user from an attribute group being revoked. To finally conclude, we presented ReTRACe, which provides efficient and authorized transaction rewrites with the support for revocation and traceability. We also presented the two novel components, RFAME and RCHIT, which are independently applicable to other systems. Thank you.